Well, welcome everyone. This is Mrs. Hanson welcoming you to Organic Chemistry. This slide is reminding you if you've not yet had a chance to go through the course information module, it is critically important to do so before starting Module 1. Remember to read through your course syllabus and view your course calendar, making note of all due dates. We're very firm with our due dates as we know that no late work is accepted. So just make sure that you're checking out all of those important due dates so you don't miss them. You'll want to review the Cornell note-taking method, which is a requirement for submitting notes. You'll read those study tips for chemistry students. You need to enroll in your Wiley Plus homework assignment, kind of our complimentary site. And then, of course, read through the information regarding our Proctorio, our remote proctoring service, and download and practice using that Chem Scanner app. Remember, if you have any questions, don't hesitate to send me an email. Give me a quick question and I'd be happy to help you with that. So let's go ahead and begin Chapter 1, a review of general chemistry. Our first chapter is going to highlight many topics from your general chemistry course from both first semester and second semester. So our goal or overview this chapter is to review some relevant concepts from your Gen Chem course. It should already be familiar to you, but I like to go through with deep detail and practices. You'll focus on the central role of electrons in forming bonds and influencing molecular properties. So let's go ahead and take a quick peek at those learning objectives. I'm just going to slide that forward here and take a look at our learning objectives. And I know that this is small, but that's okay because I just pulled them from your e-learning site. We need to compare and contrast organic and inorganic compounds. You'll describe the structural theory of matter, a molecular formula, and compare it to a structural formula. You'll compare ionic bonds with polar covalent bonds and nonpolar covalent bonds based on electronegativity. We'll describe the shape and phases of S and P atomic orbitals and practice writing electron configurations. You'll describe a bond and turn the valence bond theory and explain how sp, sp2, and sp3 hybridized orbitals form. We'll use the Vesper theory to assign molecular geometry. We'll describe the dipole moments in calculating the ionic character of a bond, that electronegativity difference used to determine if it's polar covalent, ionic, or nonpolar. And then we end that chapter with a discussion on all intermolecular forces, such as dispersion forces, dipole-dipole, and hydrogen bonding. Do any of those sound familiar from your Gen Chem course? I hope so. The activities and assessments pulled from e-learning. Of course, you know every chapter has the following requirements. To create a handwritten outline of Chapter 1 following the Cornell note-taking method. And we describe those 4 sections of the note page as you're taking notes from class. You'll compile all those pages onto a single document for uploading into your Dropbox using Chem Scanner. A non-graded practice but highly recommended is the Orion to build mastery. It's non-graded, but most students who do this find just high success in the course. Then, once you've mastered the objectives, dive into your Wiley homework assignment. Remember that this is a firm due date. The solution manual is key there to give yourself feedback as you work through those required assignments. And of course, the proctored multiple choice quiz also due by the due date. When I say proctored, it is still online, but it's proctored through our remote service called Proctorio, and you've read about that. And since this is the first chapter, I just wanted to quickly remind you what I mean by the Cornell note-taking. So this is literally the design of the page as you go through our lessons together. So each section, and I don't mind if you use more than one page here for each section, or if it's a smaller section, you can put several titles up in this beginning area. So I know 1.1 is just an intro, and 1.2 talks about organic chemistry. So if they are small sections, you can certainly put many titles up there. We're looking for the vast majority of the page to be notes that you take with me during class, during these online videos, or reading from your text. In this left margin area, you're leaving yourself room to denote important topics you need to come back and learn more about. Perhaps there is a key word you need to come back and define. Comments about this is important, or a question I might have. And then the last part, which is the bottom area, 5 to 7 lines, just summarizing the key. Edit that out, but I apologize if you were watching that with me. Organic chemistry, section 1.1. We know that it's the study of carbon-containing molecules and their reactions. So I know that that's key. Organic molecules contain carbon. And typically you find other elements such as hydrogen with that carbon. We understand that organic chemistry, or chemistry in general, talks about a collision theory in which molecules collide, bonds are breaking, and new bonds are forming, and that truly is the heart of a chemical reaction. So when we talk about a chemical change, we have new bonds that are forming and bonds that are breaking. And what's interesting in organic chemistry is we use these electron push arrows, always representing what's happening with the electrons. The heart of organic chemistry is tracking electrons and to learn how, why, and when those electrons flow during the reactions. Here we see an electron-rich oxygen in the hydroxide polyatomic ion. And here we see a positively charged carbon atom just based on electron distribution, that the electron density is being pulled towards the iodine, leaving the carbon a little bit positive. The electron-rich oxygen is attracted to the electron-deficient carbon, and we see this bond breaking where the iodide is now left on its own. We have formed a new bond between the carbon and hydroxide, and we broke a bond between the carbon and iodide. Those types of interactions are going to be key for us as we watch and learn about organic chemistry. Section 2 is known as the structural theory of matter. The structural theory of matter truly defines substances by a very specific arrangement of atoms. Here we have an example of 2 different compounds. One is known as dimethyl ether, and one is known as ethanol. When I look at this formula for dimethyl ether, I see a CH3 group attached to an oxygen attached to another CH3 group. And I know that oxygen will have 2 sets of lone pairs to complete its octet. CH3O CH3 is written in its condensed formula. Do the same for ethanol, and we see a CH3 group, a CH2 group, and an OH. This is known as a functional group as an ether, and this is called a functional group of an alcohol with the OH, and here we have an ROR. Those functional groups will be coming up soon in a later chapter, so I'm going to sprinkle them in whenever possible. When you reduce down this formula, notice that there are 2 carbons, that there are 6 H's, and there's an oxygen, C2H6O. Same thing over here. When we reduce this down, C2H6O. These 2 compounds, although they have the same molecular formula, they're hooked together in a different order, making them constitutional isomers. And that is a very important key term. It will come up over and over again in future chapters. Those are compounds that share the same molecular formula, even though their connectivity is quite different. And because they have those atoms connected in a different order, they have very different chemical and physical properties from one another. So substances are not only defined by what elements they have, but how they're connected together. That's the heart of the structural theory of matter. And according to this theory of matter, we can predict how many bonds an element will have just based on its location on the periodic table. Remember that carbon is in group 4A. Group 4A tells me that it has 4 valence electrons. Therefore, we can see carbon very readily can form up to 4 bonds to complete its octet. Nitrogen, who lives in group 5A, has 5 valence electrons, and therefore you can readily see that it has open for bonding 3 spots. 3 valence electrons are looking for partners to form bonds with. Here we see oxygen. Oxygen lives in group 6A, and group 6A tells me it has 6 valence electrons, and therefore you can see that it has available 2 open spots for bonding. And here, this is what any halogen is representing as X, or in group 1A, which, here, these are group 7A, or hydrogen, which is in group 1A. Hydrogen has 1 valence electron, therefore it has room for 1 bond. Any element X, let's just say fluorine, with its 7 valence electron, has just 1 open spot for bonding. So you can clearly see a pattern in the periodic table. 4 valence electrons, 4 spots for bonding. Group 5, 5 valence electrons means 3 spots for bonding. 6 valence electrons means 2 open spots for bonding, and 7 valence electrons leaves it 1 open spot for bonding. Noticing that we want to complete the octet as we form bonds. The octet rule helps guide us in determining structural formulas. So the structural theory of matter is used to predict connectivity and give us physical and chemical properties of the atoms building up organic molecules. So let's try. This is one from your homework called Skill Builders 1.1. We're asked to draw all constitutional isomers that have the molecular formula of C3H8O. So we're kind of thinking about how many valence electrons each atom has, how many bonds it's able to form, and trying to place those in all possible orders to come up with constitutional isomers. Let me give an example. One possible way is to hook the 3 carbons together, forming a straight chain of 3 carbons. We could then place an oxygen at the end, and then remember to use the hydrogens really as putting them on as peripherals, just to really fill the octet of all of the remaining atoms. So for instance, since carbon requires 4 valence bonds, it would require 3 hydrogens to complete the octet. This carbon in the center already has 2 bonds, so it requires 2 hydrogens to complete the 4 bonds it needs. Same here, this hydrogen and this hydrogen complete that carbon's 4 valence bonds. And that has given us 1, 2, 3, 4, 5, 6, 7. And that means that we have room to complete the octet of oxygen by placing a hydrogen off this, and we'll learn that this is an alcohol functional group. We don't know that yet, but we will. OH is a hydroxyl alcohol functional group. So that's one way we could make C3H8O. Can you think of another way? Pause the video and play with this formula and challenge yourself to practice valence bond theory and see how many different ways you can organize this compound. Start the video when ready. Well, let's see what you found. I drew this one just a moment ago with you. That was our very first, where carbon number 1 contained the hydroxyl group. When I say carbon 1, I'm numbering 1, 2, 3, and placing those hydrogens on each of the carbons to complete the octet. Remember, these O's also have valence electrons, kind of showing them how they complete the octet. So I'm labeling that as 1 propanol on carbon number 1. We could place an OH group. What else could we do? Well, we could still have our 3 carbons in a row, but instead of having the OH on carbon 1, we could have placed it on carbon 2. 1, 2, 3, 4, 5, 6, 7 hydrogens complete each of the carbon's required 4 bonds. And we know that the OH is a bond and oxygen has 2 sets of dots. So I call that 2-propanol because on carbon number 2 we see the alcohol group. And what else did you find? What about putting the oxygen in the chain itself? Carbon needs 4 bonds. That tells us we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, just exactly the number we need, and we place the oxygen within. So we're going to just practice knowing that a 2-carbon group, we'll learn, is called an ethyl group, and a 1-carbon group will be called a methyl group. Alphabetizing this, we get a functional group called an ethyl methyl ether. An ROR functional group. I am trying to sprinkle in future lessons coming up shortly here in our next few chapters. So I found 3 different ways to organize and find constitutional isomers for that particular molecular structure. And you'll have homework asking you to do the same thing. Draw all the constitutional isomers with the molecular formula C3H7Cl. C4H10. Again, I'll recommend pausing this video and trying those out. Try them out and try connecting those so that you create octets for all of the required atoms. Start up when you're ready to practice and check your work. One way that you connected those 3 carbons was in a straight chain, and you placed a chlorine at the end. You used the hydrogens to complete the octet on the carbons, and don't forget to put in the valence electrons on the chlorine to complete its octet. All of these hydrogens that were used create carbons with 4 valence bonds. I call that 1-chloropropane. As we learn, carbon number 1 has a chlorine on it. And there are 3 in a row, and we'll learn that that 3 has an abbreviation of prop for its prefix, propane. And what about if you put chlorine on the second carbon? Here we had 2-chloropropane as I draw in all of those hydrogens to complete the octet for each of the carbons. I can place carbon to chlorine on number 1, or carbon to chlorine on the second carbon. And what about thinking about butane in terms of the C4H10? You could put all 4 carbons in a row, complete all of those hydrogens, and we end up with CH3, CH2, CH2, and then a CH3 at the opposite end. We're learning that 4 carbons will have the prefix but, as in butane. And then you could think about branching. What if we only had 3 carbons in the longest chain and we placed a second carbon off of the middle of the longest chain? You'd have CH3 at each end and only 1 more hydrogen needed for that second carbon's octet. So here you would have something called, on carbon 2, we have a methyl, so 2-methylpropane. Excellent work. How about one more? C4H10O. This one will challenge you because there are 7 structures to draw. Pause the video and see if you can't figure out 7 different ways to hook 4 carbons, 10 hydrogens, and an oxygen. And come back when you're ready to check. Well, let's compare some to see if we come up with the same answer. One structure you most likely drew is 4 carbons in a row with an alcohol group. C4H10O can be drawn as 1 butanol. On carbon number 1, we have an alcohol functional group. You could move that alcohol functional group to carbon number 2 and have what's called 2-butanol, and each of the remaining bonds are then linked to hydrogen. In a third, you could have branched to where you had 3 carbons in a row, placed a methyl group, and carbon number 2 could have the OH. Completing the octet for each carbon means that we're just putting in the hydrogens, and it comes out to a total of 10. Now remember, even though I'm not drawing them, that's what you understand to be there. So we have hydrogens on each of those, giving us all 10 that were required. So we had 1 butanol, 2 butanol, 2 methyl, 2 propanol. Oops, that one I just drew here. And I think I skipped one, so let me put that over here. We could have had the methyl group on carbon 1 and called that an alcohol group as well. So when I'm drawing those structural lines, those are all connecting to hydrogens. So I could place the alcohol on the branched carbon on carbon number 1, and I can place the branched carbon on carbon number 2, the alcohol there. Then we could start making ethers. We could make the oxygen become part of the chain itself. CH3O, CH2, CH2, CH3 completes the requirements, so C4H10O. That is methyl propyl ether. We could also place the carbon attached to the oxygen on the second carbon of that group. Now see what I'm doing? 1, 2, 3 straight chain, but I could also attach it to the second carbon, and that's a unique structure. Complete the octet by just placing all the hydrogens you need to make sure carbons always have 4 bonds. Then the last idea you could do is a completely symmetrical molecule, diethyl ether. CH3, CH2O, CH2, CH3 completes all of the choices for the constitutional isomers as C4H10O. How'd you do? It's kind of fun. It's like a little game. I'll pause the video here and come back when you're ready for the next section.